Okay. This is the best New Yorker cartoon. Full stop. Okay. Or at least this is my favorite New Yorker cartoon. This will actually be relevant later. These are the ISIS forms. We're going to do those at the end. One thing that I need to apologize for is not picking up a box of pencils on the way in. But before, I should announce this now so get it into your brain. If you fill out one of these forms with anything other than a number 2 pencil, no one will read it. Scantrons only work with pencils. Don't ask me why. That's just how they work. Okay. So Tuesday, we started talking about undecidability, and today we're going to finish up talking about undecidability. And what I want to do at the beginning of the lecture today is I want to walk through one more time the reduction argument that I used to prove that deciding whether a given Turing machine accepts anything at all is undecidable. Partly because I think it went by a little bit fast last time, and partly because no matter how slowly it goes by the first time, it almost never goes in. And partly because, as someone pointed out to me after class, the proof that I showed you had a bug. So it was a subtle one, but still it was there. So I need to do this again. Okay, but I'm going to start by just thinking about a somewhat simpler problem. Okay, so let's suppose that you have a favorite Turing machine, M, which is, of course, out of focus. No. Right, and you have a string W. Okay, and so I want to describe an algorithm that will, a new Turing machine, that will accept its input if and only if M accepts W. Okay, so I'm going to build a new Turing machine, which I will call M prime, such that M prime accepts its input, whatever that input happens to be, if and only if M accepts W. Remember, M and W are things that you've fixed. So maybe, M is iTunes and W is all about that base.mp3. Maybe M is GCC and W is GCC. Maybe M is this projector and W is this piece of paper. It's just something that you've nailed to the wall. It's fixed for discussion from now on. Now I want to build a new machine that has this bizarre behavior. This new machine, because it's a machine, it has an input. It has to do something with it. Yeah?
I'm just curious. I think we've been talking. I talked with the TA.
Yeah.
But like, it's hard to understand this concept of
Okay, so let me describe to you the following machine. It's a machine that takes as input an integer, and it spits out as output an integer. Give me an integer. 7. Give me another integer. 7. Give me another integer. 7. Give me another integer. 7. I have to accept an input because that's part of the definition of the Turing machine. There's something on the initial tape. That's built into the definition of the model of computation. But the Turing machine is free to toss the input out of the window. Okay? It doesn't have to, think hard about what to do with the input if, in order to accomplish the goal for the machine, the specification of the machine that I'm building doesn't use the input in any reasonable way. If the specification of the machine is return 7, then whatever you give me, I'm going to toss it out of the window, and I'm going to return 7. Okay? So here is my pseudocode for M prime. Now, M prime needs to accept an input string. I'll call that input string X. Okay? There it is. I toss X out of the window, I write W onto the tape, and then I pass control off to my favorite Turing machine, M. Okay, so this machine has the property that for any string X, M prime accepts X if and only if M accepts W. And what's weird, what's uncomfortable is the idea that, well, the theorem has X in it. Somehow M accepting X must mean that, M prime has a reason to accept X. That M prime is actually basing its behavior somehow on the string X and deciding that X is good. But that's not what it means. What M accepts X means is that when you feed X in as the input, eventually the machine lights up the green light bulb. It may not light up the bulb because of some feature of the input. It may just always light it up. It may just never light it up. Right? So in terms of the sort of cartoony pictures that I've been describing earlier, what I want to imagine here is I have this magic machine M, and I have no idea what it does or how it does it. But I'll draw the usual rainbow here. I don't have any idea what's going on inside this box, and I can't care. But what I'm going to do is imagine, well, it's some input W, and maybe M will accept. Maybe M will reject, and maybe M will just infinite loop and never go anywhere. And now I want to build a new machine around it that's going to take in a string X and accept it if and only if M accepts W. So the way I do that is like that. Here's my new machine, M prime. I take the input X, I toss it out of the window, and then I do what I was going to do anyway. Now, this new machine, M prime, notice the string W is hard-coded into the source for M prime. The machine M is hard-coded into M prime as a subroutine. Okay? So if W is really, really, really long, then M prime is going to probably need a lot of states in order to write down the string W before it passes it off to M. If W is really short, then I'm not going to need that many states to write down W before I pass it off to M. But regardless, whatever W is, there is some finite number of states that I can use to write W on the tape, and then pass control into M, which also has a finite number of states. And so if I, pushed really hard, I could actually describe exactly how to do this with a Turing machine. Given a Turing machine M and a string W, I could build a Turing machine M prime that has this behavior. Okay. Now, the more interesting thing, and one of the things that is part of the confusion for these reduction arguments that I give, that we've been doing for undecidability, is the reduction itself, you're writing an algorithm, and one of the things that the algorithm does is build M prime. So, you know, when I say build, what I actually mean is write a program where the input is the encoding MW, where M is a Turing machine, W is a string, and the output is the encoding of a Turing machine, that has the following behavior. For any string x, M prime accepts x if and only if M accepts W. Okay? Now, we could imagine sort of doing this by hand, doing this ourselves, by writing down this bit of pseudocode here, or writing a cartoon, or implementing as a Turing machine. And so far when we've been talking about reduction arguments, where you take a black box and you build a bigger algorithm out of it, the actor who is performing the reduction is us. I am explaining a reduction to you. I am describing to you how to transform M into M prime. I'm changing the rules of the game very slightly now by insisting not only do you describe to me how to do it, but you describe to me how to do that transformation by writing code that performs that transformation. Okay? So this is a kind of preprocessor that you might stick in front of a compiler. A piece of source code comes in the front door, that's MW, and a different piece of source code comes out the end, that's M prime. And you want to do this in a way that guarantees certain relationships between the behavior of the source code you were the program was given and the behavior of the source code that the program writes out. Okay. Now, in terms of, you know, if I were doing this in Python instead of in Turing machine, this would just be a matter of writing the two-line wrapper function around whatever Python source code you gave me for M. And I would get a bigger piece of Python code called M prime. Okay. And so if you can imagine, you know, given the source code for M, you could write the source code for this bigger program, M prime. You can imagine doing it, and you can imagine it's sort of a mechanical process for doing it, which means you can sort of imagine there's an algorithm that does it, which means that you can imagine doing it with C or C++ or Python, which means you can do it with the Turing machine. Okay? So one of the things that happens inside the reduction that proves that the language never accept is undecidable is I'm going to build a Turing machine that has this behavior. Okay? All right. So now, having said that, you know, I'll come back to this in a second. Let me walk through the overall argument again. Okay. So I'm going to take as given that the following language is undecidable. Okay. Given a Turing machine and a string, I want to know whether M accepts that string. And remember, it's not enough just to run M on input W, because there's the possibility that M will infinite loop. And I want basically whatever the language that decides needs to say, hey, no, it's not going to accept because it's going to infinite loop. Okay. And that's not actually possible. And what we want to prove is that this language, never accept encodings of M such that M accepts nothing. I want to prove that this is undecidable. Okay. So what I'm going to do is what I do whenever I want to prove that a certain task is hard. I assume that it's easy and I derive a contradiction. Okay, so in order to start the proof, I have to suppose I have a Turing machine which I will call NA that decides this language never accept. Okay, or perhaps fans of Adventure Time would name this machine Lemon Grab, because it never accepts. People who are not fans of Adventure Time are looking at me very strangely. Just Google Lemon Grab, you'll get it. Okay, so I need to decide, I have this magic black box that decides the language never accept, and I'm calling this this black box NA. And I want to build around it a new Turing machine that decides accept, which is impossible. Okay? So I want to build a new machine called accept. Now, the input to the Turing machine that decides accept must be one of these pairs of strings where the first part of the first part is the encoding for a Turing machine, and the second part is the input to that Turing machine. And then somehow I need to transform it into the encoding of some other Turing machine M prime. Okay. Now, there in the middle, I have a machine that I'm going to, an algorithm that I'm going to write here, a piece of code that I'm going to write that takes in this code and its input and produces this piece of code. Right? This is exactly this. Okay? The program that I want to write to start the Turing machine A, the Turing machine A is going to start by taking the string MW as input and producing the string M prime as output, subject to these conditions. The conditions are that the program that is output, the Turing machine encoding that is output by my pink box, has the property that it accepts its input if and only if the Turing machine that came into the black box M accepts the string that came into the box, W. Okay? So M prime accepts X if and only if M accepts W. And how does that work? Well, I write a piece of code that writes a piece of code that does this. It takes the input string X, tosses it out the window, and then feeds the hard-coded string W into the hard-coded Turing machine M. And then finally, and this is the part that I screwed up last time, there are three things that, actually, sorry, there are only two things that can happen as the output of this machine NA. NA decides something, and so what that means is no matter what comes into this Turing machine, the Turing machine is going to halt. It will either accept or it will reject. There's no possibility for this machine NA to infinite loop. Okay? And now what I'm going to do to route the output of NA to the correct output of the Turing machine A that I'm building is I actually need to swap the accept and reject states. So what I will do is I'll take this, whatever this machine NA is, I know that it has an accept state and a reject state. I'm just going to quietly reach into the code for NA and swap them. Again, you know, the code for NA is a string. I can write a piece of code that, you know, looks at the encoding and finds the word reject and finds the word accept and writes the word accept wherever it sees reject and vice versa. Okay? All right, so this, I claim now, is this resulting Turing machine, right? A decides the language accept, which is, of course, impossible. Okay? So in order to finish the reduction argument, I need to argue that this reduction is actually correct. Okay? But I need to pause here and make sure that at least a little bit, that this is a little bit more clear now what the roles of the 4 different machines which are on the table are. So there are 4 Turing machines on the screen right now. There's the Turing machine NA, which I assume exists and that I assume decides the language never accept. All right, this is a hypothesis for the contradiction proof to go through. There's the Turing machine A that I am building around NA, which ultimately I want to decide accepts, and that will conclude the contradiction proof. There's the machine M, which is part of, whose source code, whose encoding, is part of the input to Turing machine A. This is a machine whose accepting behavior A is claiming to decide. There's the machine M prime, which is what is the machine that's going to be fed into NA, which NA is claiming to decide whether or not M prime can accept anything or not. And I suppose technically there's the machine that's represented by this pink box, which I haven't given a name, which is a program that takes in a Turing machine on the left and a string and spits out a Turing machine on the right, subject to this kind of behavior. Okay? Yes?
So is the pink box something that's like definable, or is that something saying like it could be
No. So the stuff here that's written in black, this NA, this is given. This is magic. It comes down from the sky on stone tablets. The stuff here in pink, this is stuff that I did myself. This is code that I write. I wrote the code to, return, not whatever NA returns. Just swap, accept, reject. Now, given the machine, what I'm deciding is I'm going to write a piece of code that has this behavior, right? I am going to solve this problem. I'm going to imagine that I'm writing something that looks like a compiler. It reads in a piece of source code. Hopefully the code is written in a language that's easy to parse, like Turing machines are. And then I can go in and muck around with the source code as if it's just a text file to change it into the source code for a different program. Okay. One point of confusion here is this machine M is playing 2 roles simultaneously. One is M is a program. It runs. It takes in input and it accepts and rejects it. On the other hand, it's really, for purposes of this reduction, it's just a string. And it's a string that I can manipulate. I can insert stuff into, and I can pull stuff out of, and I can replace all the zeros with ones, and I can put it in reverse order, anything else I want. Yeah? Yeah? Here is how X and W are related. You throw X on the floor, and W is your favorite string. They're not. W is, okay, so at the outermost level, W is part of the input to Turing machine A. Okay? Then inside this pink box is a program that's going to expect W as part of its input. And it's going to spit out a new machine M prime. X is the input to M prime. Okay? So one analogy that you might think of here is, think of the machine that's coming in the front door as a cheese grater, and the thing that goes out the back as a vegetable peeler. Given an arbitrary cheese grater, I want to turn it into an arbitrary vegetable peeler. The string X is a cucumber. It's a thing that I'm going to peel. There's no, when I'm designing a factory that manipulates kitchen implements, I don't worry about the food that those implements are going to be used on later. When I design a compiler that manipulates a piece of code, I can't think about the input that code is later going to be run on. Okay? So think of it, if you like, as this way. I'm writing code called A now. 10 years from now, somebody is going to feed in a Turing machine M and an input string W into that code that I've written called A. 50 years from then, somebody is going to come up with a string X and feed it into M prime. But by then, A is already done. And what I want to be able to guarantee now is that I can predict the behavior in 60 years when somebody feeds in whatever string X into the string M prime, by guaranteeing that, well, it just depends on whether M accepted W 10 years from now. Okay. Another way to think about this. I'm writing a story, and within that story, I have a character, that's this pink box, that itself is writing a story, one of whose characters is the string X. Okay. I'm not actually writing about X. I'm writing about somebody who's writing about X. Right? Now, these analogies about levels of indirection and so on, one of the horrible things about these analogies is they work really well to enforce your understanding if you already understand. For any particular person in the room, there's a good chance that the analogy is like, what are you talking about cucumbers for? What are you smoking? Yeah.
Okay, so I'm going to ask a question about your analogy.
Sure.
You can't grate cheese with a vegetable peeler. You do have.
No, but you know what the transformation is? You give me a block of cheese, I throw it on the floor and pull a cucumber out of the refrigerator and then shred it. That's how I build my vegetable peeler out of a cheese grater. Right? See this? See this? This word here? Any string X. X is anything at all. The answer to how is X related to W is I don't care. X is just some string that at some future point some mythical person might give to this mythical machine. I don't care. The behavior of M prime does not depend on X at all. It just doesn't matter. Nevertheless, there's this equivalence that I need to maintain that does depend on W. It does depend on M. Right? What's related here are the machines, M and M prime. X and W, totally unrelated. M and M prime, very closely related.
So is the pink box?
The pink box is this program. In fact, just to drive this point home, I'm going to write a program P, and I'm going to name this pink box P. P for pink, P for program. Yes?
When would the solution to these problems take a different form?
I'm sorry?
When would the solution to these problems take a different form? Like, when would it be different?
Some level, never. What's going to vary are two things. What goes on inside this pink box, and what you do with the arrows at the end. Right? This is just like an NP completeness reduction. The difficult part is figuring out how to transform one kind of input to a different kind of input. The cartoon looks the same for every reduction. You get a graph coming in, and you go brrr, and you get a three-sat formula coming out. Right? You get a graph coming in, brrr, and you get a different graph coming out. But there's some condition that the input and output graphs have to satisfy. They have to be related to each other. The same is true here. The input MW and the output M prime have to be related in a certain way. And the way that they're related is this. Yeah. P does not run M. P transcribes the source code of M to create the source code of M prime. He takes the .c file and writes out a new .c file. It never actually runs the program. But if you were later to run the program that it outputs, it would have this behavior. So now let me actually walk through one step at a time why this works. Okay? So there are two cases that I need to think of. Case one. Suppose M accepts W. Well, if M accepts W, then when I feed this into the machine, P is going to spit out a machine M prime that will accept everything. Okay? No matter what input M prime gets, it will accept it, because M prime accepts X if and only if M accepts W. And I've assumed that M accepts W. Okay? This is by the definition of M prime. Okay? So this means that the encoding from M prime is not part of the language never accept. Remember, the definition of the language never accept is all Turing machines that accept nothing. But here I have a Turing machine that accepts everything. So this is just by definition of the language never accept. So this means that NA rejects M prime, because NA is a Turing machine that decides the language never accept. If you feed it a string that is not in the language, the Turing machine will reject it. Right? And again, this is by the definition of NA. And now, because I do this output swap at the end, this implies that A accepts M. And this is, again, by the definition of the Turing machine A. If M accepts W, then A accepts the pair MW. On the other hand, suppose M doesn't accept W. Well, if M doesn't accept W, then M prime doesn't accept anything. Because whatever X you feed in, it's just going to throw it out the window and say no. M didn't accept W, no, nah. I don't like you. Just forget it, okay? But that means that the encoding of M prime belongs to the language never accept, because that's what the language never accept is. But that means that the Turing machine NA accepts the encoding of M prime, because that's what NA does. But that means that the Turing machine A rejects its output because of the swap at the end. So each of these implications is just by the definition of some stage of the construction. Yes?
Okay, so M is source code, right?
M is source code.
Where is it getting compiled? Where is it getting compiled?
It's never being compiled and run to see if it accepts anything. But it is a fact that if you were to run it, it would accept or not. This is a fact which I do not need to run the code in order to make the fact true. Right? Here is a piece of C code. If I run GCC on it, it will halt. I know this because I proved that GCC always halts. I didn't actually have to compile this piece of code. Here's an algorithm that computes Fibonacci numbers. I know that if I feed in n equals 12, it will spit out f of 12 equals 144. I don't actually have to write this code and run it and feed in the integer 12 to know that. Okay? So if I were to run M on input W, one of two things would happen. Either it accepts or it doesn't. I don't know which is going to happen. So let's see what happens if M accepts W, and let's see what happens if M doesn't accept W. These two cases are exhaustive. Either M accepts W or it doesn't. There's no third option.
Well, but if there's more options for what M accepts?
Well, no. Look, if I hold up one of my hands, it's either my right hand or my left hand. It doesn't matter which hand you're holding up. If I hold up one of my hands, it's either my right hand or my left hand. So if I can prove something happens when I hold up my right hand, and if I can prove that something happens when I hold up my left hand, I'm done. Then that will be considered as part of case one, I raise my right hand. If I raise my right hand, then I can conclude that M prime will accept its input.
You don't have to ever look at M prime.
Well, because I know what M prime does. I don't have to think about I don't have to consider the possibility of what if M prime does something else. I wrote M prime. I know what it does. If M accepts W, M prime says yes. There's no maybe it does something else. It doesn't. There's the code. Okay. Each of these steps follows from one of the pieces of this puzzle that we put together into this picture. The behavior of M prime tells me the behavior of M prime. The behavior of M prime tells me the behavior of NA. The behavior of NA tells me the behavior of A. And so if I put these two cases together, what I conclude from this is A accepts the string MW if and only if M accepts W. In other words, this Turing machine decides the language except, as I claimed. And here we have our contradiction. Okay? Now I'm going to give another example of this. And when I give the other example, I'm not going to go through it in quite as fine detail because of time. But one of the things that will fall out of the second example of this style of argument is a hammer which you can use to avoid doing this. Okay? This is a hammer that you can use to avoid ever having to, well, for some classes of problems, having to go through this reduction argument at all. Okay? So the specific kind of question that I want to think about is questions of the form, tell me whether the language that this Turing machine accepts has some interesting property. Okay? So I'm going to just define a set L, script fancy L. This is just going to be a set of acceptable languages. This is a set of languages, each of which is accepted by some Turing machine, that is neither empty nor all acceptable languages. So, for example, L could be the set of all finite languages. L could be the set of all regular languages. L could be the set of all languages that contain the string Binky. L could be the set of all languages that have exactly 3 elements. L could be the set of languages that contain only palindromes. Okay? The only 2 sets of languages that I want to avoid are no language at all and every language. Okay? Now I'm going to define a problem. This is the language of all Turing machine encodings such that the language accepted by that Turing machine is in L. So, for example, if L is the set of all regular languages, this trying to decide this language is asking, is the language accepted by Turing machine M regular? So basically, I can put any adjective I want after the question, is the language accepted by this Turing machine blank? Okay. The only 2 questions that I don't want to consider are what happens when L is empty. Well, then I'm saying, this is one of the things I want to avoid. So, except in of the empty set is decidable. Always say no. Whatever language your Turing machine accepts, it's not an element of the empty set. It may be the empty set, but it's not an element of the empty set. Okay? So this is one way to think about it is you might ask the question, does this Turing machine accept any palindrome? When I'm looking at the language accept in of empty, what I'm really asking is, does this Turing machine accept Discover? No. Discover isn't a language. Discover is a credit card. The answer is just no. So there is a program that just rejects, that decides this language. Similarly, if I say except in all decidable languages, this is decidable. This is like asking, does this Turing machine accept a language? Well, yes. Every Turing machine accepts a language. It's the set of strings that it accepts. Okay, this is just part of the definition. So it's decidable by the algorithm that just always says yes. For any other set L, this language is undecidable. Every language every non-trivial property of languages is undecidable. For every other set L, except L is undecidable. Okay, this is something called Rice's theorem. So the three questions that you got in lab yesterday. Prove that the set of Turing machines that accept all palindromes, prove that that's undecidable. Rice's theorem. There is a Turing machine that accepts all palindromes, and there's a Turing machine that doesn't accept all palindromes. The end. Right? Prove that deciding whether a Turing machine accepts exactly 3 strings is undecidable. Rice's theorem. There is a Turing machine that accepts exactly 3 strings, and there is another Turing machine that does not accept exactly 3 strings. Right? So once I have Rice's theorem in my hand, it's just a fairly big hammer, because it means any question you want to ask about the language that a Turing machine decides is either trivial to answer or impossible to answer. And the distinction is just, do you have a Turing machine where the correct answer is yes, and another Turing machine where the correct answer is no? So I'm going to zoom through the reduction because it's more or less the same outline that we've seen before, and the details are in the notes. So I'm going to assume that I have a Turing machine that I'm going to call AIL that decides the language except in L. A Turing machine is going to come in, and I'm going to get yes or no out. And I want to transform this into a Turing machine that decides the halting problem. Right? If you remember the halting problem, what comes in is a machine M and an input string W. And what comes out, again, is either acceptance or rejection. Acceptance if M halts on W, and rejection if it doesn't. The way I'm going to do this now is, again, I'm going to write a piece of code that transforms the incoming code MW into a piece of outgoing code I will call WTF that will have the property that M halts on W if and only if the accepting language of WTF has this property L. It lives in the set L. Okay. So now I'm going to imagine that because this set L is non-trivial, there is a Turing machine that says that accepts a language in L, accepts a nice language, and there's a Turing machine that accepts a not so nice language. Let me just assume, for the sake of argument, that the empty set is not a nice language. It is a symmetric argument if the empty set is nice, but just to keep it simple, let me assume that the empty set is bad. So L might be something like, is the language infinite? And then I have some other Turing machine Y such that whose accepting language is nice. So here's what WTF is going to do. It takes in a string X. First, I run M on W. Then I run Y on X. Now, when I say first I run M on W, this is the M that came in the front door of H and the W that came in the front door of H. This is the source code that I was given at the beginning. Now, there are two things that can happen. Either M halts on W or it doesn't. If M doesn't halt on W, I will never get to the second line of this code, which means WTF will never halt. which means, in particular, the accepting language of WTF is empty, which means the accepting language of WTF is not in L, which means AIL will reject it. On the other hand, if M does halt on W, then it's like that part just didn't matter. WTF has exactly the same behavior as Y. In particular, WTF accepts the same language that Y accepts, which means WTF's accepting language is in L, which means AIL will accept it. So if I follow this logic through, and the argument is in the notes, what falls out is H accepts MW if and only if M halts on W, which is impossible because there's no Turing machine that can decide the halting problem. Okay. So I don't expect this particular proof to go in. What I do want you to be able to do, and what we'll spend some time in lab tomorrow doing, is actually applying Rice's theorem. So, for example, there's a bunch of examples in the notes again, but let me give you one. Here's a language. I want to know, is it possible to recognize Turing machines that accept the empty tape, accept the empty string? And the answer is no. The answer is, this has to be undecidable. Because I can describe a Turing machine M1 that accepts nothing, and I can describe another Turing machine that accepts everything. And that means that this property of the language that I'm searching for isn't always yes and isn't always no. The empty set doesn't contain the empty string. But sigma star does. And so, at this point, you just say, Rice's theorem. It's undecidable. I just need to give an example of a Turing machine for which the correct answer is yes, and another Turing machine for which the correct answer is no. And that's enough by Rice's theorem to show that this question about the Turing machine's language is undecidable. Okay? Surprisingly often, one of these two machines is going to be the one that accepts everything, and the other is going to be the one that rejects everything. So, as another example, somebody give me an example of a regular language. Okay. Do you write a Turing machine that accepts that language? Scan, if I ever see anything that isn't a zero, reject, otherwise accept. Okay, good. So there's a Turing machine that accepts a regular language, and so if I feed M1 into here, I should get yes. Can you give me an example of a non-regular language? I'm sorry? Right, okay. 0 to the n, 1 to the n for all n. Could you write a Turing machine that decides that language? If I give you a string, can you tell me whether it starts with a bunch of zeros and ends with the same number of ones? Sure. Okay, done. It's undecidable. Okay, so whatever the adjective is here, as long as you can come up with an acceptable language that adjective applies to and another acceptable language that adjective doesn't apply to, Rice's theorem says deciding whether a Turing machine accepts a language like that is impossible. Which means you get a lot of two-line proofs that don't involve pictures like this. Yes?
How is it that you can...
So the theorem itself says for any set of acceptable languages that is not all acceptable languages or no acceptable languages, the question, does this Turing machine accept a language in that set, is undecidable. So all I have to do is convince you that the languages that you're talking about here are neither everything nor nothing. So here's an example yes, here's an example no. That's enough. Right? Now if I open up the box, I grind through the proof, you know, I could do everything that I do with Rice's theorem. I could expand into a reduction argument that looks like this. But nobody likes reduction arguments, so we don't have to.
Why?
There's one subtlety here. L has to be a set of acceptable languages. It has to be a set of languages accepted by Turing machines. So I can't, for example, say, you know, think about the set of all Turing machines that accept unacceptable languages. I'm going to give you a Turing machine. I'm going to ask you, does it accept an unacceptable language? Now, there are some acceptable languages and there are some not acceptable languages, but the answer to my question is, no, of course it doesn't accept an unacceptable language. By definition, whatever language it accepts is acceptable. Right? This is why the technicality that you need a Turing machine that is in this set and a Turing machine that is not in this set. Okay. Now, there's one last point that I wanted to make before passing out the forms. Too bad. So, I'll have to ask the TAs to say something about this in section tomorrow. Okay. Now I'm scared because I just spent the last hour describing the single most confusing thing in the course. And now I'm going to pass out ISIS forms. So I'm going to go ahead and pass these out. Just don't start filling them out yet because I'm not actually supposed to be here. When they get to the end of the row, pass them back to make sure that everybody gets some. And there'll be extras, don't worry about it. Okay. I need somebody to volunteer to take the filled out forms to the academic office after everybody's done. Okay, thank you. The envelope is right here, just make sure everything's in it. So before you start, a couple of technical things. What goes into my quote-unquote transcript are the averages for question 1 and question 2. This is the data that gets reported to me, to my department head, to the university. If I ever get put up for some sort of promotion or something, that gets dragged out and put onto the table. Those are the most important numerical things to answer. Otherwise, spend your time on the back of the page. What is by far the most valuable to me and to future instructors for this course is as detailed comments as you can offer on what you think we did well and what you think we did badly. When I say we, I really mean I. There will be separate forms for you to evaluate the TAs in lab tomorrow. So when it says the weaknesses and strengths of the instructor, that means me personally, not me and the rest of the staff. Comments about the rest of the staff are welcome, but you may want to actually give them directly to the staff in question. The other thing that I want to point out, by computer science department policy, box 5 on the front of the form, you're required to flip a coin, and if it comes up heads, leave it blank, and if it comes up tails, fill them both. Now, just don't fill it in. The worry is that there are too few female students that to guarantee that your responses will be anonymous if you actually fill in this bubble honestly. So don't fill it in at all. Right? We don't want to have anyone be concerned about whether their responses really are anonymous. I'm happy to answer questions. I will tell the joke that I always tell at this point, which is there's this thing called the Jedi mind trick. Those are not the droids you're looking for. I will cheat by applying the Jedi mind trick. I am a very effective instructor. This is a very useful course. Your favorite integer is 5. Now, the interesting question to ask as you walk out of the room is, if I know that he's doing that to manipulate our ISIS scores, I know in particular that he's telling a joke at the end of the class to make us laugh.